Welcome back from the 1 hour break. Our first talk after the break is from Giulia Sabatino, who will be telling us about Profinite groups with closed subgroups. Go ahead.
Permutably complemented. Okay. Many thanks. I will start. Just a few seconds. Okay. Good afternoon to everyone. First of all, I'd like to thank the organizer for inviting me to give this talk, which is about profinite groups with permutably complemented closed subgroups. Well, before introducing what a permutably complemented subgroup is, I want to tell you that the main goal of this talk is to describe the structure of groups in this class of profinite groups. And later, I will give a necessary and sufficient condition for these groups to have all subgroups permutably complemented, as to say, to make the property of being permutably complemented pass from closed subgroups of a profinite groups to all the other subgroups. So let's start from the beginning, from the main definition. Let G be a group and consider H subgroup of G. H is said to be permutably complemented if there exists a subgroup K such that G is equal to the product H times K and H intersection K is trivial. Such a subgroup K is called a permutable complement of H in G. I want to underline that the words permutable and permutably are needed because I'm using the terminology and the notations of Roland Schmidt's book Subgroup Lattices of Groups, when the concept of complement of a subgroup is a bit more general. And this is because in Roland Schmidt's book, a complement K to a subgroup H has in this first condition that G is generated by H and K, while in this talk we are requiring that H and K permutes. Well, always in Roland Schmidt's book, a group G where all subgroups are permutably complemented is called a C group. The structure of C groups is well known. Indeed, both Sernikova and Emaldi proved that a group is a C group if and only if it can be decomposed as a semidirect product of two subgroups B and A, both of them abelian, which can be further decomposed as direct product of subgroups of prime order. Moreover, if A is the normal subgroup in this decomposition as a semidirect product, the factors of A are all G invariants, that to say they are normal in G. Many years later, many group theorists got interested in studying groups in which a particular family of subgroups satisfy this property of being permutably complemented. This is the case, for example, of De Giovanni and Franciosi, who studied groups in which every finite subgroup is permutably complemented or more generally complemented. In recent years, other group theorists like Ferrara and Trombetti studied groups of infinite rank where all subgroups of infinite rank have this property, and they proved that provided that the commutator subgroup of such subgroups have infinite rank, then all subgroups are permutably complemented. And this theorem gives us a first clue to the fact that both the behavior of the commutator subgroup and the behavior of subgroups that are large in some sense in a group influence the property of being permutably complemented of all the other subgroups. Indeed, last year, I proved that if G is an uncountable group and all large subgroups, that means the subgroups whose cardinality is the same as the whole group are permutably complemented, then when the commutator subgroup is large, that's to say it has the same cardinality as the group, and the second commutator has no large simple section, then G is a C group. In particular, when the group is locally nilpotent, we have that the property of large subgroups passes to the small subgroup, hence G is a C group. So what about the profinite setting now? What about this property? What about the family we are going to investigate? Of course, the family of subgroups, which is the most important in profinite group, is that one of closed subgroup. Indeed, if G is a profinite group, a subgroup H is closed if and only if it is a profinite group. Among closed subgroups, we can find some subgroups that are large in some sense. the so-called open subgroup, which are precisely the closed subgroups which has finite index. So in the profinite setting, if a profinite group is infinite, these open subgroups share with G the cardinality. So some natural question arises motivated by the definitions and the theorems I have mentioned before. The first one is, what are the profinite groups in which every closed subgroup admits a closed permutable complement? The second one is, what about profinite groups where all open subgroups have a closed permutable complement? Well, before answering this question, let me show you this example of profinite group. If P is a positive number and we consider the Cartesian product of groups Gn where each of which is isomorphic to the cyclic group of order P, we have that this is a profinite group because of course it is a Cartesian product of finite groups. It is an FP vector space because every element has order P. Indeed, it is an elementary abelian P group. And if we remind what the structure theorem of C group says, we have that an abelian group is a C group if and only if it is a direct product of elementary abelian groups. So in particular, this group G is a C group. It's not so difficult to say that here we can find some maximal subgroups which are not closed, so they are not open. Anyway, since we are in a C group, we have that this kind of subgroup, pick one of them and say and call it M, are permutably complemented. So if we call H a permutable complement to M in G, we have that this H has as cardinality the index of M, which is P. So H is a closed subgroup with M as a complement. For this reason, we have that H is a closed subgroup which has no closed permutable complement. So I want to add a new question to the one that I mentioned in the previous slide. If every closed subgroup admits a permutable complement, is it true that it admits a closed permutable complement? Well, to answer these three questions, we introduced a class of profinite groups, which is constituted by all that profinite groups in which all closed subgroups have a closed permutable complement. So in this class, we are assuming the most as possible because we are assuming that this permutable complement have to be closed. And we studied the closure properties of such a class, comparing them with the closure properties of the abstract class of C groups. And we found a lot of similarity, like both of them are closed under subgroups, even if when we argue in the profinite setting, we study the profinite setting, we have to consider closed subgroup. The same for quotient, both of them are not closed under extension. And the most important one is the following. While C groups are closed under forming Cartesian product of finitely many C groups, we have that the Cartesian product of an arbitrary family of them of a profinite C group is still profinite C. In particular, the two closure properties that you can see in blue implies that the inverse limit of profinite C groups is still profinite C. This is why such an inverse limit can be seen as a closed subgroup of a Cartesian product of the same profinite C group involved in the inverse limit itself. And this observation was a key observation to prove the following theorem, which clarifies a lot what a profinite C group is. A profinite C group is precisely a group in which every open subgroup has a closed permutable complement. So we can restrict our attention only to open subgroups. Moreover, we don't need to write close here because if we consider an open subgroup, it has finite index. So any complement of an open subgroup has to be finite, so it is closed. Moreover, these groups are precisely groups in which where we can find a fundamental system of neighborhoods of the identity consisting of open normal subgroups, such that for every open normal subgroup in this fundamental system of neighborhood, the quotient is a C group. Moreover, a profinite C group is an inverse limit of finite C groups. This point 6 is really important. This is because if we consider the structure of C groups, we know both how C groups and how inverse limits behave. So in this way, through this point 6, we were able to find how a profinite C group is structured. In particular, from point 6 follows that the profinite completion of a C group is a profinite C group. This is because if we consider the profinite completion of a C group, it is an inverse limit of finite C group. So point 6 allows us to say that it is a C group, even if the converse is not true because of a matter of cardinality. Always point 6 ensures that like C groups are metabelian, also profinite C groups are metabelian. In particular, the topological closure of the commutator subgroup is an inverse limit of groups, of finite groups which are isomorphic to a finite quotient of the commutator subgroup of a C group. So it is an inverse limit of a billion group, so it is abelian. So we are able, thanks to this theorem, we are able to answer the 3 questions I mentioned before. And what are the profinite groups in which every closed subgroup admits a closed permutable complement? Well, this is nothing but the definition of profinite C group, but it is the same to say that these groups are all all groups, all profinite groups where open subgroups have a closed permutable complement. Moreover, if we assume that closed subgroup admits a permutable complement, it is always true that they also admit a closed permutable complement. Well, let's move to the main section of this talk, which is the description of the structure of profinite C groups. Well, to describe it, we need the concept of internal Cartesian product, which is very similar to the usual Cartesian product we know. Let G be a profinite group. We say that G is the internal Cartesian product of a family HI of its subgroup. If these HI are closed normal subgroup of G, G is the topological closure of the subgroup generated by this HI. Moreover, if we consider the subgroup generated by the Hj but one, we take the topological closure and we intersect all of them, we have that this intersection is trivial. Of course, if we consider a usual Cartesian product of groups, it can be seen as an internal Cartesian product of some of its subgroups. Anyway, the converse is also true, because in profinite groups by Wilson, we can find this isomorphism theorem, which says that up to isomorphism, the internal Cartesian product and the external one are the same object. Indeed, G is isomorphic to the Cartesian product of some of these subgroups HI regarded as groups. Moreover, the isomorphism, which is used to prove this result, sends every Hj in capital Hj in the tuple, which has Hj at J's position and 1 elsewhere. For this reason, we are going to use the same notation both for internal Cartesian product and the usual one. Now we are in the position to find out how profinite C group behaves, starting from its abelian closed normal subgroup. Why do we start from them? Because, as I said before, profinite C groups are metabelian, and the topological closure of the commutator subgroup is abelian. So, the first step is to understand how this topological closure of the commutator subgroup behaves. Well, if G is a profinite C group and A is an abelian closed normal subgroup of G, we have that this subgroup A contains minimal closed normal subgroups of G, which are of prime order. Moreover, A can be seen as a product of G invariant subgroups of A of prime order, where G invariant means normal in G. As a particular case of this lemma, we have that a profinite group which is abelian is profinite C if and only if it is an internal Cartesian product of subgroups of prime order. And this will be very important in determining the structure of a profinite C group also in the general case. Indeed, now that we know how the topological closure of the commutator subgroup is, we were able to prove that a profinite group is profinite C if and only if it can be decomposed as a semidirect product of two closed subgroups, which are abelian, each of which is a Cartesian product of subgroups of prime order. Moreover, if A is the normal subgroup of this semidirect product, all the factors in this decomposition of A are G invariant. Furthermore, A can be chosen to be the topological closure of the commutator subgroup. Indeed, here we use that G over this topological closure of the commutator subgroup is abelian, so the complement of this subgroup is a direct product, or a Cartesian product, sorry, of subgroups of prime order. Well, now we can notice how profinite C groups and C groups have a similar, very, very similar structure. Indeed, it was expected because profinite C groups are inverse limit of finite C groups. What is the difference? The difference is that while for C groups we have a semidirect product of abelian groups which are direct product of prime order groups, the direct product is replaced by the Cartesian product in the profinite setting. In particular, we have that C groups have to be torsion because B and A are both torsion. In profinite C group, this is not true in general. They are not necessarily torsion. Indeed, if we consider this group, which is the Cartesian product of all the CP, where CP is the cyclic group of order P with P running in the set of all positive primes, we have that it is a profinite C group because it is a Cartesian product of prime order groups. And if we consider the tuple, where in each entry we find the generator of the corresponding cyclic subgroup, this element is not periodic. So this profinite C group is not periodic. So another question will be added to the previous one. What about torsion profinite C group? Is it true that a profinite C group is a C group if and only if it is torsion? For this reason, we started investigating the behavior of torsion profinite C groups, starting, like in the previous case, from the abelian profinite C groups. And we found out that if A, which is a Cartesian product of these subgroups of prime order, is a profinite C group, it is equivalent to say that it is a C group, that it is torsion, and that it is of finite exponent, and the exponent is square-free. Let's say why. Of course, as I said before, a C group has to be torsion. Let's look at this structure and assume that A is torsion. Of course, we have that there are only finitely many primes involved as orders of these cyclic subgroups, because otherwise we find ourselves in the same condition of the previous counterexample, with the risk of finding non-periodic elements. So for this reason, there are only finitely many primes involved. And if we consider the least common multiple of these primes, it is precisely the product of all of them, which is also the exponent of A. So A has square-free finite exponent. On the other hand, if we consider a group of finite exponent, which is abelian, it is a direct product of finite cyclic subgroup. Since this exponent is square-free, each of the cyclic subgroup has a square-free order, so each of them can be further decomposed into a direct product of prime order subgroups. Hence, A is a direct product of cyclic subgroup of prime order, which is a C group thanks to the structure theorem. So question D has a positive answer in the abelian case. What about the general case? Let's see the following example to study the general case. Consider P and Q two positive prime numbers such that P is equivalent to 1 modulo Q. And then for every natural number n, let's consider Gn the subgroup generated by two elements xn and yn, where xn has order P, yn has order Q, and the subgroup generated by xn is Gn invariant. This is a C group because of its structure, because as you can see, it is a semi-direct product of a group of order P and a group of order Q. So let's consider the Cartesian product of all these Gn. if we consider the Cartesian product of all these Gn, it is a Cartesian product of C group, so it's profinite C. Moreover, it has finite exponent because the exponent is PQ. Anyway, if we consider its subgroup that we call A, generated by all the xn, this is a Cartesian product of the xn. And if we assume by way of contradiction that G is a C group, then any of its subgroups is a C group, in particular A is a C group. Hence it has to be written, decomposed as a direct product of some G invariant subgroups of prime order. Anyway, it's not so difficult to show that the any G invariant cyclic subgroup of A are the Xn. So A has to be a direct product of some of these Xn. Moreover, A is infinite, so it has to have cardinality Aleph 0. Anyway, A is profinite, and its cardinality is 2 to the Aleph 0. So for a matter of cardinality, A cannot be a C group. As a consequence, G is not a C group. So the condition to be torsion is not enough for a profinite C group to be a C group. For this reason, we investigate the behavior. So in general, the answer to this last question is no. And to find a necessary and sufficient condition for a profinite C group to be a C group, we investigated the behavior of profinite C groups which are C group. And we used this decomposition given by the structure theorem, using the fact that this kind of group have finite exponent because these two factors have finite exponent. So each of them has finitely many non-trivial C-low propy subgroups. If we choose one C-low propy subgroup of the permutable complement of this and one C-low propy subgroup of G prime bar, we have that their semidirect product is still a C group. Moreover, we used the fact that the psilopropy subgroup of G prime bar has to be written as a Cartesian product of G invariant cyclic subgroups of order P. And through this structure, we found that centralizer of P in Q has finite index. So in particular, the centralizer of G prime bar in K has finite index in K, but this is equal to this index. On the other hand, since our group is a semidirect product of two abelian groups, we have this condition on the center. So we have that the index of the subgroup given by the product of the center and the topological closure of the commutator subgroup has finite index in G. Since the converse is also true, we provided a necessary and sufficient condition for a profinite C group to be a C group, which is to be torsion and to have this index finite. All the results I've mentioned can be found in profinite groups with complemented closed subgroups, which is a joint work with Gustavo Fernández Alcober. And it can be found on arXiv. I thank you for your attention.